Last spring, a neighbor showed me his new residential solar installation. It was 32 dark blue panels gleaming on his roof, a heavy aluminum inverter on his garage wall, and a digital monitoring screen connected to his phone. It cost him over $32,000. But as we stood there, a gentle spring breeze drifted across his yard, barely rustling the leaves of a maple tree. I looked at the panels, then down at his screen. The solar output was dropping under a passing cloud, and the wind, a continuous force moving right through his property, was doing nothing for his home. The modern energy industry has trained us to look past that wind, or to believe harvesting it requires a giant, spinning three-bladed turbine that costs thousands of dollars and draws endless noisy complaints. Contrast that with a completely different scene. Last August, I drove out to a small dairy farm outside Berlin, Ohio, owned by an old-order Amish builder named Eli Miller. Eli's farm has no electrical lines running from the road. There are no high-tech screens and no $30,000 loans. Yet inside his milk house, his cooling tanks were humming steadily. His well pump was drawing clean water, and the workshop lights were bright. Walking outside to the south side of his large hay barn, he pointed to 4 narrow, vertical wooden columns bolted to the gray siding. They didn't have blades or propellers. They looked like simple rectangular chimneys, about 4 feet tall and a foot wide, with a narrow vertical slit running down the front face. There was no visible movement, but as I stepped closer, I could hear a low, steady hiss, the distinct sound of rapidly moving air trapped inside a hollow chamber. When I held an anemometer up to that slot, the ambient breeze across Eli's open pasture was moving at 12 miles per hour. But the air pulling through the inside of that wooden box was rushing past the sensor at nearly 31 miles per hour. Stop and think about that. A simple wooden box, built from materials available at any local lumberyard, was taking a breeze so light it wouldn't even turn a standard commercial turbine, and accelerating it 3 times over to produce steady electricity. Understand this, energy itself is not complicated. The forces of nature, the sun, the water, the traveling air, have been doing the heavy lifting of human civilization for thousands of years. What is complicated is the modern economic model designed to sit between you and those forces, ensuring that every kilowatt hour you consume comes attached to a monthly invoice. We have been taught to forget simple solutions because a $90 box sitting on a barn wall is a direct threat to a centralized utility model that relies on total consumer dependence. The device on Eli's barn is a variation of a forgotten design, older than the modern electric grid. In the autumn of 1922, a Danish engineer named Poul La Cour had been dead for 8 years. But a small wooden box he built in Askov, Denmark, was still operating perfectly. It used no external blades. Instead, it relied on an internal pressure differential to spin a lightweight rotor, powering 4 light bulbs on nothing but moving air. By 1925, the United States Department of Agriculture published the technical specifications in Farmer's Bulletin number 470. Thousands of farmers across the Midwest used it to build their own home power plants. This knowledge didn't disappear because it stopped working. It died when the federal government ran subsidized power lines to the countryside between 1936 and 1955. Small independent systems were replaced by the convenience of a monthly utility bill, and the old bulletins were quietly pulled from circulation. The technology wasn't disproven, it was simply made invisible. To understand why this box works where modern bladed turbines fail, we must look at a basic principle of fluid dynamics described by Giovanni Battista Venturi in 1797. Think of a common garden hose. Open wide, the water pours out in a heavy, slow stream, but if you place your thumb over the opening, restricting the path, that same volume of water is forced through a much smaller space. The velocity shoots up dramatically. This wooden box does the exact same thing with the air currents crossing your roof. Wind enters a wide vertical slot and hits a carefully angled internal baffle. This wall, forces the incoming air through a constriction only 1/3 the size of the original opening. By the time the wind reaches this narrow internal channel, its speed has multiplied dramatically. Let us be honest about the practical limits. If you expect one box to run a central air conditioner and a clothes dryer all at once, you will be disappointed. This is a localized offset system designed to harvest low-velocity wind between 3 and 6 miles per hour. The exact wind standard turbines consider useless. Traditional bladed designs need a starting speed of 7 to 9 miles per hour just to move their heavy blades. This box, with its lightweight internal parts, begins producing current at 3.5 miles per hour. If your home sits in a deeply forested valley where the air remains completely stagnant, this device cannot help you. It needs movement. But if you can stand in your yard on a typical afternoon and feel the breeze against your face, the resource is there. The structure itself is straightforward, but its effectiveness relies entirely on absolute precision within its internal geometry. To build it, you require a single sheet of exterior plywood, a few lengths of threaded steel rod, and a low-revolution alternator you can source online for under $40. The magic lies in the specific angles of that internal baffle wall and the exact placement of a small aluminum impeller that catches the accelerated airstream. If you've cut the plywood even half an inch off the specified dimensions, the internal air column will stall, and the impeller will remain perfectly still. Let me show you exactly how to lay out the first lines on the plywood, how to shape the internal compression channel, and how to wire the generator so that the very next breeze crossing your roof belongs entirely to you. Lay your sheet of 3/4-inch exterior grade plywood flat across 2 stable sawhorses. Take a moment to smell the wood, that sharp, clean scent of fresh pine resin. It represents the foundation of your independent power supply. Before you pick up your saw, understand this. A project like this does not require complex machining, but it demands quiet, focused precision. The biggest mistake beginners make is rushing through the layout lines, assuming 1/8 of an inch won't matter in a wooden structure. In fluid dynamics, a slight deviation can turn a smooth, accelerating column of air into a chaotic swirl of turbulence that robs your generator of its power. Let us begin with the main body, the vertical column. You will need to measure and mark out 2 side panels that are exactly 4 feet tall and 8 inches wide. Next, mark out your front and back faces, which are 4 feet tall and 14 inches wide. As your circular saw bites into the wood, keep your hands steady and let the blade do the work. Watch the fine, pale sawdust pile up on the floor. When you finish these 4 long cuts, you have the outer skin of your wind box. Set them aside for a moment and look at the front panel. Down the center of this face, you need to cut a clean, vertical intake slit exactly 1.5 inches wide, stopping 6 inches short of both the top and the bottom edges. This is where the wind enters, and its edges must be sanded smooth down to the bare grain, so the air does not catch on any rough splinters. Now, we must build the heart of the device, the internal venturi baffle. This is the angled wall that forces the air to accelerate. I prefer using a sheet of lightweight, malleable aluminum, about 1/16 of an inch thick, because it will never warp from moisture and has a dull, silver gleam that lets you see how the air will slide along its surface. If you cannot find aluminum, a thick piece of dense cardboard, heavily saturated with clear amber epoxy, works just as well. You will bend this sheet to form a long tapering wedge inside the box. The wide mouth of the wedge starts right behind the front intake slit, and it narrows down until it forms a tight throat that is exactly 1/2 inch wide near the top section of the column. Stop and think about what happens inside this throat. As the air gets squeezed into this small space, it cannot slow down because more air is pushing in right behind it. It has no choice but to speed up. But here is where a common mistake happens. Beginners often make the angle of this baffle too steep, creating a blunt wall rather than a gentle slope. If the air hits a sharp barrier, It bounces back, creating a pocket of dead pressure that chokes the intake. The slope must be a long, gradual incline, tapering smoothly over 3 feet of the column's height. Think of it like a boat hull slicing through water. You want the air to glide, not collide. At the very top of this narrow throat, where the air velocity reaches its absolute peak, is where you will mount the permanent magnet alternator. When you source this, look for a low-revolution unit, often sold for small hydroelectric setups. It should feel heavy in your hand, a compact cylinder of cold steel and copper wire with a smooth, unyielding weight. On its shaft, you will bolt the internal impeller. This is not a fan blade. It is a dense, multi-vaned aluminum wheel that looks identical to the compressor wheel inside an automotive turbocharger. It sits entirely enclosed within the narrow throat of the column. When the accelerated air column hits those tightly curved aluminum vanes, it forces the wheel to spin at high revolutions, even in a light ambient breeze. Before we seal the box together, we must prepare the wood against the elements. The interior of this chamber will see every kind of weather: humid summer mornings, freezing driving rain, and thick autumn fog. Take a can of marine varnish. When you open it, you will notice a pungent, heavy chemical smell, thick with solvents and resins. Using a wide brush, apply 2 thick, even coats to every square inch of the plywood, both inside and out. Watch how the clear liquid sinks into the dry wood, turning the pale pine a deep, rich golden honey color. Let it dry completely until the surface feels hard and smooth as glass. To handle the inevitable condensation that forms when warm air hits the cold internal baffle, drill 4 small 1/4-inch holes through the bottom floor of the box. Take a small scrap of brass wire mesh and staple it tightly over these holes on the inside. This allows any trapped water to drain away naturally while keeping spiders and insects from climbing inside and building nests that could jam your impeller. Now lay the back panel flat and apply a thick, milky white bead of waterproof exterior wood glue along the edges of the side panels. Screw the sides to the back using 3-inch galvanized deck screws, spaced every 6 inches. You should see a small amount of glue ooze out of the seams like thick cream. Wipe it clean with a damp rag. Slide your aluminum baffle into its precise position, securing it with short screws from the outside of the side panels. Then glue and fasten the front face over the top. The structure should feel incredibly solid, a heavy, silent column ready to face decades of weather. Finally, look at the electrical leads coming from the bottom of your alternator. They are usually thick copper wires jacketed in heavy black plastic. Bring these wires out through a small hole drilled near the top of the back panel, sealing the exit point with a glob of clear silicone sealant to keep it watertight. These wires carry low-voltage direct current. It is completely safe. You can touch the bare copper with your bare hands while the unit is running, and you will not feel a thing. Run this wire down the side of the column using small insulated staples to keep it neat. This line will connect directly to your basic charge controller, a small plastic box, with a digital face that regulates the flow of electricity into your battery storage system. The mistake here is using wire that is too thin, which creates resistance and turns your hard-earned electricity into useless heat before it ever reaches your battery. Use heavy 10-gauge copper wire. It has a thick, substantial feel and ensures that every single electron harvested by the windbox makes its way safely down to your battery bank. Your box is now fully assembled, sealed against the rain, and wired for power. It sits on your workspace, a silent testament to traditional self-sufficiency, waiting only to be lifted into the path of the wind. Now that the wood is sealed and the glue has cured, let us look deeply at why this specific shape commands the air so effectively. To understand the science here, you do not need a background in engineering. You only need to observe the natural world around you with a patient eye. What is happening inside this vertical column is rooted in fluid dynamics, specifically the elegant relationship between the speed of a moving fluid and its internal static pressure. And remember, to a physicist, Moving air behaves exactly like moving water. It follows the same laws, seeks the same paths, and responds to compression in the exact same manner. The primary mechanical principle at work inside our wooden chamber is the Venturi effect, an offshoot of Bernoulli's theorem. Stop and think about an everyday occurrence you have likely witnessed in a narrow alleyway or between two large barns on a gusty afternoon. Out in the open field, the wind may feel like a gentle, lazy breeze. But the moment you step into the narrow gap between those two solid structures, that same breeze transforms into an aggressive gust. The air has not multiplied. Instead, the massive volume of air traveling across the landscape has encountered an obstacle and is forced to compress itself to pass through the restricted opening. Because the air behind it keeps pushing forward with relentless momentum, the air inside the restriction must speed up to let the volume pass. Let us look at a simple analogy. Picture a wide river flowing calmly across a flat meadow. The water moves slowly, almost imperceptibly, but downstream, the river encounters a narrow gorge where two stone walls squeeze the channel down to a fraction of its original width. The water does not pile up. Instead, it rushes through that canyon with fierce velocity, churning as its speed multiplies. Once it clears the gap, it instantly slows down again. Your wooden wind box is that stone canyon. The wide mass of air crossing your yard enters the vertical slit and strikes the long, sloping face of the internal baffle. We are forcing a 14-inch wide column of air into a tight throat that is only 1/2 inch wide. By the time the wind reaches this constriction, its static pressure drops significantly, and its physical velocity shoots upward by a factor of 3. This sudden pressure drop creates a powerful localized vacuum right at the throat of the column, spinning the small multi-vaned aluminum impeller. Now, let us speak with absolute candor about the hard boundaries of this method. I refuse to give you the exaggerated promises that are so common in modern energy advertisements. Every tool ever forged by human hands has its limits, and if you do not understand where this wind box fails, you will waste your time and your materials. Understand this. This device is a specialized solution designed for a specific niche, and it is not a magic cure for every household bill. First, consider environmental conditions where this method will not work. This box relies entirely on the natural movement of the atmosphere. If your property is situated in a deep mountain hollow or a low desert basin where the air remains completely stagnant for weeks at a time, this box will sit silent. It cannot create energy out of nothing. Furthermore, look at the obstructions around your home. If your house is buried inside a thick shelter belt of mature trees that stand 40 feet taller than your roofline, you will face severe problems. Trees act like a massive comb, breaking the smooth flow of the wind and shattering it into chaotic rolling eddies. When this chaotic swirl hits the vertical intake slot, it cannot form a unified stream along the baffle. The air stalls inside the chamber, keeping the impeller perfectly still. If you cannot mount this unit in a position where it has clean exposure to the prevailing windward side of your property, do not build it. Second, let us establish an honest boundary regarding your electrical expectations. The unit we have built is an offset tool, not an industrial power plant. In an average residential wind zone with speeds hovering between 4 and 6 miles per hour, a single box will realistically harvest between 500 watt-hours and 1.5 kilowatt-hours of energy over a full 24-hour day. This is a steady trickle of power. It is perfectly suited for continuous baseline loads like high-efficiency LED lights, your internet router, communication devices, and low-draw DC appliances. But here is where it fails completely: resistive heating loads. If your goal is to run a standard electric clothes dryer, a heavy kitchen oven, or a central air conditioning compressor, this device will not help you. Generating heat requires a violent draw of current that will instantly drain a modest home battery bank. If you expect this box to sustain a wasteful consumption habit without any adjustment on your part, you are chasing a fantasy. Finally, we must acknowledge physical limitations. Plywood, even when treated with marine varnish, is an organic material. It responds to its environment, expanding in the humid warmth of summer and contracting in the dry cold of winter. This constant movement places mechanical stress on the glued seams over time. If you ignore the unit and fail to perform a basic annual inspection, checking the seals and clearing the drain screens, moisture will find a way past the sealant. Once water creeps into the wood, it will swell. The internal geometry will warp by a fraction of an inch, and the delicate aerodynamic balance inside the throat will be ruined. This box is not a modern appliance you can install and forget for 30 years. It demands a small measure of your regular attention to survive. Now that you understand the precise physics of the internal pressure vacuum, the necessity of clean air, and the realistic boundaries of what this power can do, we are ready for the final step. Bringing this device out of the workshop requires an understanding of how wind interacts with solid structures. Let us step outside and look at how to read the roofline of your home, so you can find the exact point where the air naturally compresses against your building. When you step back and look at the completed column sitting on your workspace, finished in its rich coat of amber varnish, you are looking at something far greater than a simple weekend project. You are looking at a physical inheritance. This silent box of wood and metal is a direct bridge to a lineage of master practitioners who refuse to believe that the basic necessities of human life should be complicated, expensive, or dependent on a distant monopoly. It is a piece of forgotten history that survived not because it was protected by corporate lawyers, but because it was too simple to break and too practical to ever truly lose. The true story of this design opens in the windy pastures of Denmark in the late 19th century. An engineer named Poul La Cour, whom history remembers as the Danish Edison, established groundbreaking wind experiments at the Askov Folk High School. La Cour looked at the centralized steam operations dominating Europe and saw a quiet danger. He understood that when a community surrenders the production of its own energy, it surrenders its freedom. In his 1903 lectures at Askov, he laid down the core philosophy that guides our work today. A wind machine built for the home must blend into the natural soundscape of the property, requiring only basic tools to maintain. La Cour abandoned massive external blades, focusing instead on small, enclosed aerodynamic chambers that could harness the gentle winds crossing a typical yard every single day. By 1925, the United States Department of Agriculture compiled these localized blueprints into Farmer's Bulletin number 1470. Concurrently, the Agricultural Extension Departments at Iowa State College published practical manuals in 1928 and 1933, distributing these low-cost designs directly to families across the Midwest. These bulletins were printed on plain paper and given freely to any farmer with a handsaw and a framing square. For nearly 2 decades, variations of these simple, bladeless boxes quietly ground grain, pumped water, and illuminated remote farmhouses across the heartland, operating entirely on the free air currents passing over the fields. Then, the economic landscape reorganized. Between 1936 and 1955, the Rural Electrification Administration, working with utility holding companies, ran power lines to almost every farm in America. This was heralded as a triumph of progress, but it carried a silent cost: the systematic erasure of local self-reliance. As Robert Reiter's academic history, Wind Energy in America, documents in painful detail, independent wind manufacturers, like the Jacobs Wind Electric Company, were rapidly forced out of business. The old USDA bulletins were pulled from distribution and allowed to fade from memory, replaced by corporate pamphlets instructing families how to connect to a permanent monthly invoice. The technology did not disappear because it failed the laws of physics. It disappeared because a recurring bill is simply more profitable to a utility than a self-sufficient individual. Yet, True knowledge is a stubborn thing when protected by a culture that values autonomy. While the rest of the country plugged into the centralized grid, the old order Amish communities of Lancaster County, Pennsylvania, and Holmes County, Ohio, looked at utility poles with deep skepticism. Guided by their traditional reading of Romans chapter 12, verse 2, warning against conforming to the world, they recognized that attaching their homes to a centralized wire meant surrendering household sovereignty. So, they quietly kept the old bulletins alive. For generations hidden in plain sight, Amish builders continued to construct these bladeless collectors in their workshops. They sought no patents and formed no corporations. They simply maintained a tradition of practical, affordable power because it kept them independent. Today, modern scientific research is finally validating the quiet wisdom of these traditional practitioners. For decades, utility companies pointed to macro-level wind maps from the National Renewable Energy Laboratory, claiming that residential wind was non-viable across most of the country. But a landmark 2018 study out of Penn State University exposed the flaw in that data. Researchers measured wind velocities at human scale, right at residential roof heights, across hundreds of properties. They discovered that localized wind speeds were 41% higher than macro maps predicted because those models completely ignored the natural terrain acceleration that occurs as air channels over ridges, through tree lines, and against the slopes of household roofs. The fluid dynamics Paul Lacour relied upon a century ago were confirmed to be entirely accurate by modern measurements. Understand this. The wooden box sitting on your sawhorses is not an appliance. It is an act of quiet restoration. It is a declaration that you are no longer a passive consumer in a dependent loop, but a producer standing firmly on your own ground. When you look out your window and see the trees bending in an autumn gust, you should not see an inconvenience. You should see an abundance of free energy passing over your home, waiting to be harvested. You do not need a $30,000 loan, a team of contractors, or the permission of a utility executive to claim what the sky gives you for nothing. Stop and think about the choice before you. Next month, another utility bill will arrive in your mailbox, and you will pay it because you have been trained to believe there is no alternative. Or, you can spend one quiet weekend with a saw, a sheet of common plywood, and a handful of hardware. By Sunday evening, as the wind stirs, you can stand by the side of your home and listen to that soft, steady hiss